But really, what I'm actually doing is I'm doing geophysical and geological mapping, and the essence behind that is that I make a number of observations at some point. Then what I try and do is I try and construct some image from that series of observations. Now clearly the problem that I'm having to face is, how do I join the dots? And all of you at some point in time have played that little game in the paper where you have some image and you're trying to join the dots. But what you do when you join the dots together is that you have to have some mental picture of how those dots actually join. And many times what's going to happen is, there's numbers, sometimes there's numbers, but for us, there's often, sometimes not numbers there. You know, you have to sort of visualize. So the resulting geological model often depends on the quality of the positioning information. So how good is your positioning information, and how good do you need your positioning information to be? So I thought I'd start off with a good reference point that you all should probably go back to at some point in time, and that's Natural Resources Canada, and the Natural Resources Canada's website, and the Canadian Spatial Reference System. And what the Canadian Spatial Reference System tells us is that, there's a bunch of different types of GPS receivers, this positional information that you're dealing with. You can go from recreational receiver, mapping grade receiver, geodetic grade receiver. And of course, just like everything else, you get what you pay for. When you start moving from here to here, you're starting to go from hundreds of dollars to thousands of dollars to tens or hundreds of thousands of dollars, depending on the level of sophistication that you want to get to. But it's not just as simple as that either, because the other issue that's going on here is that you have to know exactly what kind of GPS that you're going to want to use. There's all sorts of differential corrections being available to you, wide area augmentation systems, local differential corrections. Are you doing it in RTK? Do you really need real-time data? What kind of data do you need? Well, where I was going with this is that I realized that what has happened is, and I'm going to take you through a little history here, is that GPS has made this massive evolution, but GPS has actually driven a lot of things that we're doing, and it's taken us to a certain point of information that we can use now. But have we got to the ultimate point of where we can go to with some of this navigation, measurement, location technology? I suspect that we haven't. I suspect that there's a whole bunch of stuff out there that we really need to try and move to the next level. There's another level out there that we haven't got to yet, and I'm going to try and show you how we try and get to that point. So I took some stuff out of my old remote sensing class slides, and I'm sure all of you have used some of this at some point in time as well. But realistically, what you're going to do is you're going to try and use an aerial photograph, and you use an aerial photograph, and you always have to have this coverage, adjacency between an overlap between flight lines. If you want to get topographic information from this, realistically, the important thing is that you need to know where those photographs are. But when you start moving to topography, what you're actually doing is you're trying to compare results or points from individual images. And how many of you can bend your eyes around this thing? There actually is two images there. You really should be able to see the topography coming out of that. And there's this wonderful fold structure here. It's dipping off, and we see these flat irons, and we see these faults and stuff like that. We can do all of this stuff, but the problem that we end up with is how good is this thing? How good is this data? Because usually what happens is we do this correlation from one image to another, and then to actually make it into real topography, we actually have to get some ground control points. Because without those ground control points, all of this stuff is kind of floating. We don't really have absolute control on what's going on. So how good is it, folks? Well, I thought I'd show you how good it is. Because what I did is this is a little part of Newfoundland that I've been working in for quite a while. It's called the Beaver Peninsula. And it just so happens that I happen to locate a number of different data sets of topography of this area. I have the standard, what you would call toporama. You might go to toporama. You may go to Canadian Digital Elevation Data. You may call it CanVec. There's a whole bunch of names for it, but it's the standard 50-meter resolution aerial topographic data. And I also happen to look into the fact that the government of Newfoundland had actually flown a 20-meter survey in that area. We also have some SRTM of that area. Looks pretty good, doesn't it? Really, not much difference between them, is there? Why would I bother doing any effort at trying to look at any difference? Well, the problem is when you subtract SRTM from the 20-meter and when you subtract the SRTM from the 50-meter, all of a sudden you don't get a simple random pattern coming out. You start getting some really odd-looking features coming out of this thing. And I kind of smoothed this out a little bit just to try and emphasize what was going on. And lo and behold, what I'm starting to see is I'm starting to see, I can actually see the flight paths of where the photographs were. These paths that I might, I'm not learning to drive your machine yet here, Phil. It's not a geophysical tool, obviously. Geophysicist, I've got to try it and break it a few times first, and then I'll get it working.
That's okay, I have a spare.
Okay. You can start seeing that now what's happening is I've got some systematic patterns coming out of this thing, and it just so happens that the flight paths for these photographs when they were taken, guess which way they were taken? Oh yeah, they were taken flying this way. There's the flight paths. There's the individual photographs pattern that I'm actually seeing. And I haven't shown you, but I'm actually looking at 10 to 20 meters of error that's sitting in these topographic data sets. So when we start talking about topography, we've got to look at a little bit of how good the data set really is. Well, we can do topography in a number of different ways. My game is geophysics, so we do aeromagnetic surveys. And then when you do an aeromagnetic survey, the aircraft, the pilot needs to know how high you are above the ground. Because if you're too low, you may be hitting something with your instrumentation, and that's not good news because it's going to cost you. It could cost you in many different ways, but it's going to cost you one way or another. But what we do is we have this thing called a radar altimeter, which is really just a single path of the pass of the thing measuring the height above the ground. So let's look at some radar altimetry data from southern Alberta. Now, what is interesting about this one is that this was data that was collected in 1992 and 1997. 92, 97, and we had a series of flight lines and tie lines. Geophysicists like to have grids. We want grids because it's easier to work with grids. Give me a nice square block to work with. What you're actually seeing is that you're seeing the effect of the different sampling spacing and also the different quality of the GPS. The 1992 data clearly isn't anywhere near as good as the 1997 data. I've got a lot more ridges, if you will, in this lot than I do in this lot. I also have this funny block here. Hopefully some of you can see this funny block going across the top. The company had a problem with their aircraft. They brought in a second aircraft and they put the GPS at a slightly different elevation in the aircraft, in the second aircraft, and forgot to correct for it. And there it is coming out straight at you. You can see the thing that's going on. So GPS, great, but it's only good as what you calibrate it for.